Welcome to 4.10. Here we're going to take a look at how first and second derivatives can be applied to understanding real-world contexts. And we'll continue looking at motion and also kind of extrapolate those understandings to some other real-world situations. Okay, so go ahead and complete 1, 2, and 3. I know it seems like it could be a lot. It really won't be. So go ahead and go through this now on your own, spend about 5 minutes or so, and this will help propel us into working with derivatives much more fluidly. So when we're talking about motion, we're thinking about really three characteristics: the position of an object, the velocity of an object, and the acceleration of an object. And these three are all related. So if I'm given a function that models the position of an object, then the derivative, or the instantaneous rate at which the position is changing, is what we call the velocity of that object. And then, of course, the second derivative, or the derivative of velocity, will tell me the acceleration, or how the velocity is changing at an instant. So we can also consider the second derivative of the position, which is acceleration, and that's the first derivative of velocity, which will be helpful in a second. All right, so if I have a particle, it's moving along the x-axis according to the function x of t, then let's go through these quickly. Initially means that, of course, the time is equal to 0. At the origin, remember the origin is an intersection of x and y axes that are both at 0. And so in this case, the time will be 0 and the position will be 0. So x of 0 is 0. At rest means, of course, that the position is not changing. So the derivative, the rate of change of the particle, x prime of t, is going to be equal to 0, or in other words, the velocity equals 0. Now, if the velocity of the particle is positive, we associate the positive direction with movement to the right, so the particle is moving to the right. And of course, that means that the first derivative of position, which is velocity, is greater than 0. Similarly, if the particle is moving to the left, that means the velocity is negative, and thus the derivative, first derivative of position, is less than 0. To find the average velocity of the particle over a time interval, now think about this, right? What is average rate of change? Well, what I do is I take the position I'm at the end, subtract the position I started at, and divide by the time it took. So I divide the change in position by the change in time. That's just average rate of change. Instantaneous velocity is the velocity at a single moment or instant in time. And this is really important. The function v of t is telling us the velocity at any instant t. If the acceleration of a particle is positive, that means that the velocity is increasing. Remember, the acceleration is the first derivative of velocity. So of course, if acceleration, when we look at this graphically, if the acceleration is positive, that means the velocity is increasing, meaning the slope of your original function is increasing, and that results in a concave up graph. Conversely, if an acceleration of a particle is negative, then the velocity is decreasing. We know that the concavity is then concave down. And that should make sense based on our understanding of the relationship between the derivatives. In order for the particle to change direction, so think about going from right and then moving to left, or left and then moving to right, we know that the velocity is going to have to change sign. And so if you're thinking about, well, how do I determine that? Remember, we've created these really beautiful sign charts that allow us to analyze how the derivative or the second derivative is changing. And of course, when we notice that the sign changes, we'll notice that the particle is going to be changing direction. All right, how might one find the maximum velocity of the particle? Well, notice that when you're finding the maximum velocity, what you're doing is you're finding the relative extrema, or in other words, the relative maxima of your velocity function. So if you have a function v of t, your velocity, you can use the first derivative test on this function. You can actually use the second derivative test as well, but using it with this function. So I want to find the extrema of this function. So I need to take the derivative of this function, and use that derivative either with the first derivative test, or I could go to the second derivative test to find the relative extrema for this function. Now, notice, of course, the derivative of velocity is acceleration. So I'd actually be creating a sign chart for my acceleration and using that to determine where this function has a relative maxima or relative minima. So that's a really important thing to take away. What about the maximum speed? Well, notice something interesting about speed. So speed is the absolute value of velocity. So when I'm asking myself, when is the speed greatest, I'm actually asking, what is just the absolute value, the greatest absolute value that velocity ever has? So I need to consider not just its maximum velocity, its relative maximum. I'd also want to consider the absolute, sorry, I should have said absolute maximum. But I also need to consider the absolute minimum, because the speed doesn't care whether you're moving to the left or to the right. It just cares where is it traveling the fastest. And so I would take the absolute value of the absolute max and the absolute min, and whichever one was greater would be the absolute or maximum speed. All right, with that being said, let's kind of apply this in general to real life, so that we can, if we see problems that are dealing with something other than motion, we can still apply the derivative. Okay, so obviously we'll see a lot of situations with motion, but we can apply derivatives to any real life situation. And so here's how we want to consider it. So if a function f of t, and I use t here as the independent variable because a lot of times in real life we're concerned with as time moves on. So if a function f of t measures some amount or quantity at a time t, and it's important to note it doesn't have to be at a time t, but I use it here because I think it helps us contextualize it. Then the derivative, f prime of t, measures the instantaneous rate at which the quantity is changing at a time t. So, for example, water is, going into a bucket, and your function measures the height of the water or the amount of the water in the bucket. Then the derivative measures the rate at which that amount is changing. Okay? The second derivative measures the instantaneous rate at which the rate of change is changing. So this is important to note. The second derivative is measuring how the first derivative is changing. And this, of course, is interpreted as acceleration when we talk about motion, but it's also incredibly helpful when we're trying to find a maximum value for our derivative. In other words, when is the quantity changing the most? Because then we can use the first derivative test with with f prime of t, which means we'll be getting f double prime of t and using that with our first derivative test to find extreme values. So I put that here. Since f double prime is the derivative of f prime of t, we can use it to find the extreme values of f prime of t using the first derivative test. And you could also, of course, use the second derivative test here. You just need to take another derivative. So we talked about that with finding the maximum velocity just a second ago, and I think that's something that's pretty important to remember. So now, no matter what type of a situation you're dealing with, you can interpret how the derivatives will apply to that situation and use them to your advantage. All right, so let's take a look at an example problem. Of course, AP free response problems are going to have a bunch of different parts to them, and we'll see a lot of different things that they're asking, both with situations dealing with motion, as this one is, and situations that are dealing with other situations where you're measuring an amount or a quantity, and you're curious, when is it reaching a maximum value, when is it changing by the most, so on and so forth. You should be able to handle this on your own, so go ahead and try it first on your own, and then we'll take a look at it briefly together. So with any real world or any free response question, I cannot stress how important it is to make subtle annotations and to know what it is you're trying to find, to have succinctly written down all the things you know, and to have a plan going in. If not, you're going to waste an incredible amount of time by following through on something that actually won't get you the answer you want or won't get it for you efficiently. So here we know, measured in meters, time in seconds. For part A, when I read when is the particle at rest, I know exactly what that means. If something's at rest, that means its velocity is equal to 0. So I know I'm searching for when v of t is equal to 0. So immediately I'm going to say to myself, okay, set this equation up, solve for t. And this just gives me a perfect plan for what I need to do. I need the velocity function, and I need to set equal to 0 and solve. So I'm going to do exactly that. I know that velocity is the derivative of position, and this, of course, is going to be t squared minus 2t minus 3. All right, I'm going to set v of t equal to 0, so I have t squared minus 2t minus 3 equals 0. I should be able to factor this. Thankfully I can. It's going to be t minus 3 times t plus 1 equals 0. And of course this will be when t is equal to 3 and when t is equal to -1. Now, at this point, I could be done with it and move on. The problem is that I haven't answered this question. This question is an English question. It's asking me, when is the particle at rest? So I need to respond with a sentence answer. And it needs to make sense. And this is where you have an opportunity to confirm for yourself that your answer makes sense. So you can read it out and say, does that make sense? When is the particle at rest? Well, let's just say I wrote t equals 3 and t equals -1, circled it, and walked away. That would make such little sense because I'm saying that the particle is at rest when time equals -1 seconds. And that makes no sense whatsoever. Time is a positive value. So the only positive value that I'm given is a time of 3 seconds. So the particle is at rest 3 seconds after it begins moving. However, I also need some rationale. I need to explain, well, what does it mean to be at rest? It means the velocity is 0. And so what I'm saying is that when I substitute 3 in for t, I'm going to get a velocity of 0. So the particle is at rest after 3 seconds because, and I'm abbreviating here even though you shouldn't, v of 3 equals 0. Right? And of course I could go back and I could check my work here. 3 squared is 9, minus 6 minus 3 is going to be 0. And so this leads me nicely into part B. And when I read this, it says, what is the speed of the particle after 1 second? So there are a couple pieces here. The speed I know is the absolute value of velocity, and this is at 1 second. So what I'm searching for is the velocity at 1 second, but the absolute value of that velocity. So I know I'm going to need to find the velocity at 1 second and take the absolute value of that. Nothing too hard since I already have that function. The absolute value of velocity at 1 second is going to be the absolute value of 1 minus 3 times 1 plus 1. Notice that I just used the factored form version. Makes it a little easier in my opinion. I have -2 times 2, which is -4. Absolute value of that is going to be +4. So the speed after 1 second is going to be 4, and I need to include units here. That's vitally important. And so the speed after of the particle after 1 second is going to be 4 meters per second. And so there I've written it out. Notice you could say 4 meters per second or 4 m/s. Either one will do. All right, now we're on to part C. All right, so part C, what is the average acceleration of the particle over the interval 1 to 5? What does this mean about the motion of the particle? Okay, so you got a couple of easy ones. You hit them both out of the park, and you should have because you're going to need to spend most of your time just interpreting what this piece is going to ask you. So the key here, of course, is interpreting average acceleration. Okay, So let's think about an average that we're used to taking. We're used to finding the average velocity. How do we do that? Well, we take the position where we ended up minus the position where we started and divide by the time it took. And that will give us the average velocity or the average rate of change. Here, we don't want the average velocity. We want the average acceleration. Well, acceleration is the change in velocity. So the average change in velocity, and this is where I think the whole problem lies, is if you see acceleration and you say to yourself, change in velocity. Because then when you read this statement, it says, what is the average change in velocity of the particle over the interval from 1 to 5? And when you read that, you have no problem whatsoever. The average change in velocity is going to be the velocity at 5 minus the velocity at 1. That'll tell you the total change in velocity. And then to take the average, you'll divide it by the total number of seconds that it took. So, now annotating my question, knowing more clearly what I need to find, the average acceleration is going to be equal to the velocity v of 5 minus v of 1 divided by 5 minus 1. All right, so we'll go ahead and compute v of 5, v of 1, and of course divide by 4. So v of 5, I can do this pretty much in my head, right? V of 5, here's my velocity function, is going to be 5 minus 3, which is 2, times 5 plus 1, which is 6. 2 times 6 is 12. Minus the velocity at 1. Now I've actually already found this. Remember, this was negative 2 times 2, which is negative 4. I don't want the absolute value, though, because I'm not looking at speed. So 12 minus negative 4. And this will give me 16 over 4, which is 4. Now, I need the correct units here. Remember, velocity is measured in meters per second. Acceleration is measured in meters per second squared. So it would be 4 meters per second squared. Now I want to say briefly, why is this meters per second squared? And this is something that I think a lot of people just take for granted. They memorize it, they never know why. Here's why. Velocity is measured in meters per second. So when I say acceleration, what I'm really saying is meters per second, right? This is a change in velocity. So when I say I'm changing by 16, I'm saying I'm changing by 16 meters per second. But I'm doing that over the course of 4 seconds. So when I divide 16 by 4, I get 4, but the units are meters per second. Well, when I have meters per second, that's dividing all of this by seconds. Well, remember, dividing something is the same as, so I'm dividing this by this. Dividing is the same as multiplying by the reciprocal. So this is the same as saying meters per second. And of course, this is meters per second squared. So that's where that's coming from. It's important to sort of understand why that works, because now you realize, oh yeah, acceleration is the change in velocity. So it's meters per second, which is meters per second squared. All right, now I just need to write out my answer, and this is very straightforward now. The average acceleration of the particle from 1 second to 5 seconds is 4 meters per second squared. Now, what does this mean about the motion of the particle? And this is, I think, the bigger picture question that understanding will be really important just in general. What does it mean to have an average acceleration of 4 meters per second over the course of those 4 seconds, so from t equals 1 to t equals 5? Well, acceleration measures the change in the velocity. So on average, over those 4 seconds, your velocity is increasing by 4 meters per second every second, which means that the speed, right, the velocity of your particle is increasing. It's traveling faster over the course of these 5 seconds on average. doesn't necessarily mean at every instant its speed is increasing or its velocity is increasing. But on average, it will increase by 4 meters per second every second. And also this means that over the course of these 4 seconds, as we see in the calculation, that my velocity is increasing by 16 meters per second over the course of this time from 1 to 5. All right, at this point, go ahead and complete Unit 4.10 homework on Math Excel and be ready to present those problems in class.